Welcome to lecture 4 of a total of 11 lectures. This week we're going to start talking about second order linear equations. We'll cover sections 3.1, 3.2 and 3.3 in the lecture notes. Before I begin, let me announce the exams. The midterm exam will be on Wednesday the 11th and the final exam will be on Thursday the 26th. In our normal lecture time, so 2 p.m. Midterm exam will be 60 minutes long and the final exam will be 90 minutes long. Now we're going to start talking about second and also higher order linear ordinary differential equations. In this chapter, we're going to be looking at equations of the form y double prime plus some function p of t y prime plus some function q of t y is equal to g of t. P, q, and g could be any functions of t. If we just look at the y terms, there's a 1y on its own plus 1y on its own plus 1y equal to 0. So this is a linear equation. Or we might be looking at equations of the form p of t y double prime plus q of t y prime plus r of t y is equal to g of t. These equations are linear second order differential equations. If the function g is always 0, then our differential equation is called homogeneous. G is not always 0, then the equation is called non-homogeneous. First type of equations we're going to look at is homogeneous equations with constant coefficients. We're going to start by looking at the equation a y double prime plus by prime plus cy is equal to 0, where a, b, and c are constants. For example, let's suppose I asked you to solve y double prime minus y is equal to 0. We want a function y of t, which satisfies the rule that when we differentiate the function 2 times, we still have the function that we started with. So I ask you, what about e to the power t? If we differentiate this function 2 times, what do we have? We still have this function. This function satisfies the differential equation. What about e to the power minus t? What do we get if we differentiate this 2 times? Well, if we differentiate it once, we get minus the function, minus e to the minus t. And then if we differentiate it a second time, we're going to get another minus. Minus minus becomes plus. We end up with e to the power minus t, or the function that we started with. So yes, this function auto-satisfies the equation. What about a linear combination of these two functions? What about c1 e to the power t plus c2 e to the power minus t? Does this satisfy the equation? What do we get if we differentiate this 2 times? The answer is we still get the same function. In fact, this is actually the general solution to y double prime minus y is equal to 0. We have 2 functions and 2 constants. What about an initial value problem? Solve y double prime minus y is equal to 0 with the initial conditions y of 0 is equal to 2, y prime of 0 is equal to minus 1. Now, you'll note this initial value problem has a second order differential equation and it has 2 initial conditions. And these numbers are always the same. If we had a third order equation, then we would have 3 initial conditions. If we had a fourth order equation, we would need to have 4 initial conditions, and so on. We know the general solution is C1 e to the power t plus C2 e to the power minus t. We are looking for the solution which satisfies the initial condition. We want the solution which has that when t is equal to 0, y is equal to 2, and to just highlight this, and we want that at this point the slope needs to be minus 1. If we use the first initial condition, we can see that we must have C1 plus C2 is 2. Because, of course, e to the power 0 is 1 and e to the power minus 0 is 1. The next thing we need to do is we need to differentiate our solution. Y prime is C1 e to the power t minus C2 e to the power minus t. And then we use the second initial condition to see that C1 minus C2 must be equal to minus 1. We have a linear system of 2 linear equations. You know how to solve these from your linear algebra course. In this case, we must have that C1 is a half and C2 is 3 over 2. So now we know the solution to the initial value problem. Now let's go back to the general equation. Ay double prime plus by prime plus cy is equal to 0. How can we solve this? In the previous example, we used exponential functions in our solution. So we might be wondering, maybe we always want exponential solutions. Let's try that. We're going to make a guess at this point. We're going to guess that the solution looks something like e to the power rt for some number r that we don't know yet. We can differentiate this 2 times, and then we can stick these functions into the equation. And we find that we must have 0 is equal to a r squared plus br plus c e to the power rt. Now, e to the rt is never equal to 0. E to the rt looks something like this if r is a positive number. This function is always strictly positive. We can't have e to the rt equal to 0. So for this equation to make sense, ar squared plus br plus c must be equal to 0. So let's just recap. We started with equation 1, the differential equation, and now we want to choose the number r which satisfies ar squared plus br plus c is equal to 0. The second equation is called the characteristic equation of the first equation. And this is important because e to the power rt solves the differential equation if and only if the number r solves the characteristic equation. And this is our strategy. We're going to write down the characteristic equation. We're going to find r which satisfies the characteristic equation, and then we will know e to the power rt solves the differential equation. Now, the characteristic equation, ar squared plus br plus c equals 0, has 2 roots, which I'm going to call r1 and r2. And these are given by the formula minus b plus or minus square root of b squared minus 4ac over 2a. There's 3 possibilities here. Either these 2 roots are real numbers, but different real numbers, or there might be complex conjugates, or there might be real numbers but repeated, the same real number twice. We're going to need to study these three cases separately. First, we're going to study case 1. So suppose that our two roots are real numbers and they're different real numbers. In other words, we're going to be supposing that b squared minus 4ac is strictly positive. Then we have two solutions, e to the power r1t and e to the power r2t. So we can take a linear combination of these two functions, and we still have a solution. C1 e to the power r1t plus C2 e to the power r2t is called the general solution to equation 1. For example, solve y double prime plus 5y prime plus 6y is equal to 0. First thing we need to do is we need to write down the characteristic equation. And we take the same numbers. We have the numbers 1 at the front, and then 5, and then 6. Our characteristic equation will have the numbers 1, 5, and 6 in it. So our characteristic equation must be r squared plus 5r plus 6 is equal to 0. Just take the same numbers, replace y double prime by r squared, replace y prime by r, and replace y by 1. We want to find the numbers r which satisfy the characteristic equation. By factorizing it, we can see that they must be minus 2 and minus 3. As soon as we know these two roots, we can write down the general solution to the equation. Therefore, the general solution is a constant C1 e to the power minus 2t plus a constant C2 e to the power minus 3t. And that's it. That's all we need to do to solve this differential equation. Now let's do an initial value problem using the same equation. Same differential equation with the initial conditions y of 0 is 2, y prime of 0 is equal to 3. We know the general solution to the differential equation. We just need to find the constants C1 and C2. We need the derivative. This function is easy to differentiate. Y prime is minus 2c1 e to the power minus 2t minus 3 c2 e to the power minus 3t. And then we use the initial conditions. Y0 must be 2, and y prime of 0 must be equal to 3. That gives us two equations for C1 and C2. Solving these equations, we find that C1 must be 9 and C2 must be minus 7. And then we're finished. We know the general solution. Now we found the two constants, so we can write down the solution to the initial value problem. The solution to the initial value problem is 9 e to the power minus 2t minus 7 e to the power minus 3t. I've deliberately gone quite quickly here. I'll leave the calculation on this page for you to check when you have more time. Another one, solve an initial value problem. That's a differential equation, 4y double prime minus 8y prime plus 3y is equal to 0. together with two initial conditions. Y of 0 is equal to 2, y prime of 0 is equal to a half. We'll do the same strategy as before. We'll use the characteristic equation to find the general solution to the differential equation, and then we'll use the initial conditions to find the two constants. This is the first part of the calculation. In the differential equation, the numbers are 4, minus 8, and 3. So in our characteristic equation, the numbers are 4, minus 8, and 3. We find the roots of this, and we find that they must be 3 over 2 and 1 half. Doesn't matter which one you write first, which one you write second, doesn't matter. As soon as we know the roots of the characteristic equation, we can write down the general solution to the differential equation. That's constant e to the power r1t, here 3 over 2t, plus constant e to the power r2t, or here e to the power t over 2. All that's left is to find the constants c1 and c2. And I'm going to leave this for you to check. Please check that I didn't make a mistake here when you have more time. If I've made a mistake, let me know on the discussion forum. I think the constants must be minus a half and 5 over 2. And then we can write down the solution to the initial value problem. Minus a half e to the power 3 over 2t, plus 5 over 2 e to the power t over 2. So let's summarize this. To solve a second order linear differential equation with constant coefficients, we need to find two linearly independent solutions. And we do this by writing down the characteristic equation and then finding the roots of the characteristic equation. Case 1, which we've been looking at, if we have two different real numbers, then the two functions we want are e to the power r1t and e to the power r2t. Case 2, if the roots are complex numbers, we haven't done this yet, we'll fill this in later today. And part 3, if the roots are repeated, then again, we haven't done this yet, we're going to fill this in. But before we do that, I want to go off on a tangent and talk about fundamental sets of solutions. Let's go a little bit more general in this section. I'm going to be talking about y double prime plus pt y prime plus qt y is equal to 0. But this is a cumbersome notation. I want an easier way to write this. So I'm going to define a linear operator L to be two derivatives plus pt multiplied by one derivative plus qt. So for example, if I write L of y, then what I mean is y double prime plus pt y prime plus qty. So in other words, instead of writing our differential equation as I've done at the top, I now have a nice, neater, quicker way to write this. I'm going to be writing this exactly the same differential equation as L of y is equal to 0. Let's suppose we have two solutions of this differential equation, two solutions of L of y is equal to 0. Then, as every linear combination of these two functions is also a solution. And this is a very quick proof, so let's just run through this very, very quickly. I start with L of c1 y1 plus c2 y2. Put that into the definition. Two derivatives of c1 y1 plus c2 y2 plus pt, one derivative of this plus qt this. Rearrange this, and because derivatives are also linear, we find that we have c1 L of y1 plus c2 L of y2. But because y1 and y2 both solve the equation, this is just 0 plus 0. So therefore, y also solves. So therefore, c1y1 plus c2y2 also solves this differential. Something else we're going to be needing in this section is something called the Wronskian, named after a Polish mathematician. This is defined to be the determinant of the 2x2 matrix y1, y2, y1 prime, y2 prime. If I want to be careful, I'm going to be writing this as w of y1 and y2 at time t. But you will find that often in these slides, I'm just going to be lazy. And when I'm being lazy, I just write this as w. Theorem. Suppose that we have two functions, y1 and y2, which solve the differential equation L of y is equal to 0. And suppose there exists at least one time t where the Wronskian is not equal to 0. Then the set containing c1y1 plus c2y2 contains every solution of our differential equation. Now, because this contains every solution of our differential equation, this is called the general solution to this differential equation. If we have two solutions, y1 and y2, and if their Wronskian is non-zero at least one point, then c1y1 plus c2y2 is the general solution. And in this case, we say that y1 and y2 form a fundamental set of solutions to L of y is equal to 0. For example, show that t to the power of a half and t to the power minus 1 form a fundamental set of solutions to this differential equation. And just because we don't want to be worrying about square roots of negative numbers and divided by 0, we're only going to be looking at this for strictly positive t. So what do we need to do? We need to show three things. We need to show that t to the power of a half is a solution to the differential equation. We need to show that t to the power minus 1 is also a solution to the differential equation. And we need to show that these two functions are linearly independent. In other words, we need to check that the Wronskian is non-zero somewhere, at least one point. So this is what we're going to do. First, t to the power of a half. We put this into the equation, calculate our derivatives, simplify everything, and you can check that we get 0. So the answer is yes. T to the power of a half does solve this differential equation. And then we do the same thing for t to the power minus 1. Now we put t to the power minus 1 into the differential equation, and we check to see, do we get equal to 0? The answer is yes. You can check that after everything is simplified, we get equal to 0. So yes, y2 equal to t to the power minus 1 does solve the differential equation. That's the first two things done. We also need to check, are y1 and y2 linearly independent? To do that, we calculate the Wronskian. That's the determinant of the 2x2 matrix y1, y2, y1 prime, y2 prime. Put the functions in, calculate the determinant, simplify it as minus 3 over 2, t to the power minus 3 over 2. And remember, because t is strictly positive, this is not 0. Because it's not 0 at least one point, in fact, it's not 0 everywhere, we found that y1 and y2 are linearly independent. And that's all we need to do. We have two solutions, and these two solutions are linearly independent. Therefore, they form a fundamental set of solutions to our differential equation. Section 3.3 is about complex roots of the characteristic equation. Let's go back to our linear second-order differential equation with constant coefficients. Now, instead of b squared minus 4ac being strictly positive, we're going to be assuming that b squared minus 4ac is strictly negative. Then the two roots of the characteristic equation are going to be complex conjugates. And we're going to write them like this. The first one I'm going to call lambda plus I mu, and the second one I'm going to call lambda minus I mu, where lambda and mu are real numbers. Then we have two solutions. E to the power r1t, or e to the power lambda plus I mu t, is the first solution, and the second solution is e to the power r2t, or e to the power lambda minus I mu t. But what does e to the power of a complex number mean? We're going to use Euler's formula, which tells us that e to the power lambda plus I mu t is equal to e to the lambda t cos mu t plus I e to the lambda t sine mu t. Why does this make sense? To convince you this is the correct formula, I'm going to differentiate this. I'm going to differentiate e to the power r1t. Or I'm going to be differentiating e to the lambda t cos mu t plus I e to the lambda t sine mu t. There's two t's here, so we have to use the product rule on the first term, and the second term also has two t's in. So we're going to have to use the product rule on the second term as well. Don't worry about I, which is the square root of minus 1, is just a number. We could just assume this is any other number when we do derivatives. Just imagine there was the number 3 here instead of the number I. This is not going to affect our calculus at all. So, first of all, using the product rule on the first term. If I differentiate e to the lambda t, I get lambda e to the lambda t, and then cos mu t stays the same. Then I'm going to differentiate cos mu t. E to the lambda t stays the same. Derivative of cos is minus sine, and then of course we get a factor of mu at the start. And then we do the same thing for the second term. Differentiate e to the lambda t to get lambda e to the lambda t, and then differentiate sine to get cos and the factor of mu at the front. Let's simplify this a little bit. Let's gather together the cos terms and the sine terms. For the cos terms, there's a lambda at the start, and we also have an I mu at the end. So lambda plus I mu. For the sine terms, there's a minus mu just here, and we also have plus I lambda. But remember that I squared is minus 1. So I lambda minus mu is the same as I lambda plus I squared mu. But then we can take a factor of I out to get I multiplied by lambda plus I mu. But wait a minute, here's lambda I mu and here's lambda I mu. Here's an e to the lambda t. Here's an e to the lambda t. We can factor these out. And we get lambda plus I mu, e to the lambda t cos mu t, plus I, e to the lambda t sin mu t. But this is what we started with. E to the lambda t cos mu t plus I, e to the lambda t sin mu t is just e to the power r1t. So what we have is r1 e to the power r1t. Even if we have complex numbers, the derivative of e to the r1t is still r1 e to the r1t. Great. So everything is going to work the way we expect it to. However, e to the r1t and e to the r2t are functions which map to the complex numbers. They take a real number, t, and they give us back a complex number. And we don't want this. What we want are functions which map from the real numbers to the real numbers. We don't want to be dealing with complex numbers. We want the complex parts to be cancelled out so that we just end up with real valued solutions. So what can we do? Instead, we're going to be considering these two functions, u and v. U is going to be a half y1 plus y2, and v is going to be 1 over 2i y1 minus y2. What am I doing here? U is a linear combination of y1 and y2. y1 is a solution, y2 is a solution, so therefore every linear combination of y1 and y2 is also a solution. So that means u must also be a solution to a differential equation. Likewise, v is a linear combination of y1 and y2, so v must also be a solution of the differential equation. Let's calculate these. Looking at u first of all. y1 is e to the lambda t cos mu t plus I sin mu t, and y2 is e to the lambda t cos mu t, and then minus I sin mu t, because we have a minus mu there, and the sign of minus mu is minus sine of mu. But then look, plus I sin mu t and minus I sin mu t. These are going to cancel out. We're going to end up with cos plus cos, or 2 cos, and then divide by 2 to get 1 cos. U is e to the lambda t cos mu t. For v, we're going to do almost the same thing. Here there's cos mu t and then minus cos mu t. These are going to cancel out. We'll end up with I sin plus I sin, or 2I sin, divided by 2I to get 1 sin. So Vt is going to be e to the lambda t sin mu t. And as I said before, these two functions both solve the differential equation because they are linear combinations of y1 and y2. But are they linearly independent? To check they're linearly independent, we calculate the Wronskian. And I'll leave this for you to check. You can check that if we calculate the Wronskian of these two functions, we get mu e to the power 2 lambda t. Mu is not 0 because we have complex numbers. E to the power something is always not equal to 0, so therefore the Wronskian is not equal to 0. So the answer is yes. These two functions are linearly independent. We have two solutions which are linearly independent. What does that mean? That means we have a fundamental set of solutions. If we have a fundamental set of solutions, then we can write down the general solution in terms of these. So the general solution must be C1u plus C2v, or C1 e to the power lambda t cos mu t plus c2 e to the power lambda t sine mu t. Let's do an example. Solve y double prime plus y prime plus y is equal to 0. What do we do first? First, we write down the characteristic equation. The characteristic equation is r squared plus r plus 1 is equal to 0. R must be minus b, or minus 1, plus or minus the square root of b squared minus 4ac divided by 2a. We have minus 1 plus or minus the square root of minus 3, which we can think of as the square root of minus 1 and 3, or divided by 2. The square root of minus 1 is I, and the square root of 3, of course, is just square root of 3. So r is minus a half plus or minus I root 3 over 2. Okay, now we know lambda and mu. Lambda must be minus a half, and mu must be root 3 over 2. As soon as we know lambda and mu, we can write down the general solution to the differential equation. Because the general solution is always c1 e to the power lambda t cos mu t plus c2 e to the power lambda t sine mu t. For this example, lambda is minus a half, so we have e to the power minus t over 2 in both terms. Mu is root 3 over 2, so we have cos root 3 over 2t and sine root 3 over 2t. And that's all we need to do to solve this differential equation. Let's do another one. Solve y double prime plus 9y is equal to 0. We need the characteristic equation. R squared plus 9 is equal to 0, which we could factorize to r minus 3i and r plus 3i. And then we see that we must have r is plus or minus 3i. In other words, we must have that lambda is equal to 0 and mu is equal to 3. As soon as we know lambda and mu, we can write down the general solution. E to the power 0 is just 1, so we can forget about that. The general solution is c1 cos 3t plus c2 sine 3t. And that's it. Solve this differential equation. I've done it in 2 sentences. Let's do an initial value problem. Solve 16y double prime minus 8y prime plus 145y is equal to 0 with the initial conditions. Y of 0 is minus 2, y prime of 0 is equal to 1. We need the general solution to the differential equation. We'll find that using the characteristic equation. And then we will find the constant c1 and c2, which satisfy the initial conditions. Characteristic equation. Just copy the numbers, 16 minus 8 and 145. 16 minus 8, 145. And then find the roots of this equation. I'll leave this for you to double check. Please check there's no mistakes here when you have a free moment. I think we get a quarter plus or minus 3i. So lambda must be a quarter and mu must be 3. As soon as we know lambda and mu, we can write down the general solution to the differential equation. Here, C1, e to the power lambda t, or e to the power t over 4, cos mu t, or cos 3t. And then the second term is the same, except with sine instead of cos. Next, we need to find the initial. We need to find the constants C1 and C2, which satisfy the initial conditions. I've put our solution at the top. We need to differentiate this before we can go any further. Using the product rule, first I'm differentiating e to the power t over 4 to get a quarter e to the power t over 4. And then I'm differentiating cos 3t to get minus 3 sine 3t. And then in the second term, I'm doing the same thing. A quarter e to the power t over 4 here. And then differentiate sine to get 3 cos 3t. And then we use this to find the C1 and C2. First, y of 0 is minus 2. Put t equal to 0 into the equation at the top. Cos of 0 is just 1. E to the power t over 4 is just 1. And sine of 0 is 0. So we can forget about the whole of the second term. We just get C1 plus 0. So straight away we can say C1 must be minus 2. We also need to satisfy y prime of 0 is equal to 1. Remember, sine of 0 is 0, so this is all 0. This is all 0. Forget about those. Cos of 0 is 1. Cos of 0 is 1. Forget about those. E to the power of 0 is 1. Forget about this. Forget about this. And we're left with a quarter C1 plus 3 C2. We know C1 already. We have minus a half plus 3 C2. So therefore C2 must be a half. And that's what we need. We know the general solution. We know C1. We know C2. Now we can finish the question. We can write down the general solution. Sorry, we can write down the solution to the initial value problem. Minus 2 e to the power t over 4 cos 3t plus a half e to the power t over 4 sine 3t. And I can show you a graph of this solution. Y of 0 is equal to minus 2. That means we start just here. And we're also told that the slope here is equal to 1. So we're sloping upwards very slightly just here. So let's summarize what we've done today. If we want to solve a second order linear ordinary differential equation with constant coefficients, we need to find two linearly independent solutions. And then the general solution is a linear combination of these two solutions. For the first case, the case where the roots of the characteristic equation are different real numbers, then the two functions that we want are e to the power r1t and e to the power r2t. For the second case, that's the case of complex conjugates, The two functions that we want are e to the power lambda t cos mu t and e to the power lambda t sine mu t. There's a third case. What do we do if we have repeated roots, if we have the same real number twice? We'll do that tomorrow. Tomorrow, we're going to start by talking about what do we do if we have repeated roots of the characteristic equation. We will talk about reduction of order. We will talk about non-homogeneous equations, and then we'll talk about the method of undetermined coefficients. Are there any questions? It'll be a written exam. I'll give you the questions, and you'll write your answers on a piece of paper, take a photograph, and then upload the file. The exam will be 60 minutes long. I haven't decided how many questions there will be yet. There might be 2 big questions, or if I want to ask smaller questions, I might ask more of them. And the exam will be split into half. So you will get, for the first part of the exam, you'll have 30 minutes to answer the question or questions and upload your answers. And then the second exam, half of the exam, will also be 30 minutes. You'll get a new set of questions to work on, and you have 30 minutes to solve those and upload those solutions. If, as an example, if I gave you, say, a second order equation, second order initial value problem, probably non-homogeneous. Let's suppose I gave you something like this, but instead of e equal to 0, I might give you e equal to a function. I don't know, I'm just making a function up. Let's suppose it's equal to 7 sine t. Then this would be a big question, and you would have 30 minutes to solve a question like this. and there will be multiple versions of each question. So different students will receive slightly different questions.